It is early in 1943, in a Royal Electrical and Mechanical Engineers field workshop somewhere behind the lines in North Africa, and a British mechanic named Sergeant Albert Hodges is standing on the rear deck of an American-built Sherman, looking down into the engine compartment, and he does not believe what he is seeing. He has worked on a great many engines in his time. He has worked on the Liberty engines of the Crusader tanks and the Bedford engines of the Churchills, and he understands engines the way a surgeon understands the body. But he has never seen anything like the thing that fills the back of this particular Sherman. It is not an engine, it is 5 engines. 5 complete 6-cylinder automobile engines of the kind that powered family saloons on American highways, arranged in a great circular cluster around a central shaft, all bolted together into a single, dense, heavy, impossible mass of 30 cylinders. Sergeant Hodges counts them to be sure. 5 carburetors, 5 sets of spark plugs, 6 to a bank, 30 in all. 5 exhaust manifolds. 5 engines, breathing and firing and turning together, feeding their combined power into one shaft that ran forward to drive the tank. And his first thought, the thought of every mechanic who ever first laid eyes on this engine, was that it was madness. 5 engines meant 5 times everything that could break. It meant a maintenance nightmare, a tangle of complexity that would surely leave these tanks broken down across the desert. And his second thought, which came later, after months of working on the thing, was that he had been wrong. Because this absurd engine, this cluster of 5 car motors that looked like a joke, turned out to be one of the most reliable power plants the British Army operated. The Americans had built it because in 1943 they needed Sherman tanks faster than they could build engines for them, and the only way to get the engines was to take the engines they already had, by the thousand, off the automobile lines and bolt 5 of them together. It should not have worked. It worked. This is the story of how, and of exactly how 5 separate engines were made to beat as one. The problem by 1943 was not the tank. The problem was the engine, and more precisely, the gap between how fast America could build Shermans and how fast it could build engines to put inside them. The Sherman was a triumph of mass production. The factories that built it, the great tank arsenals and the converted locomotive works and the car body plants could turn out hulls and turrets and tracks and guns at a rate that astonished the world. The bottleneck was never the steel. It was the power plant. A tank needs a large, powerful engine on the order of 400 horsepower, and large, powerful engines were exactly the thing that America did not have in surplus, because the same engines the tanks wanted were the engines the aircraft wanted, and the aircraft had first priority. The standard Sherman engine, the Wright radial, came from the aircraft industry, and the aircraft industry needed every radial it could get. The better tank engine, the Ford GAA V8, was still being developed and was not yet flowing in the numbers required. The diesel twin from General Motors was being sent to the Soviets, and meanwhile the demand for Shermans only grew as the Americans equipped their own expanding armored divisions and supplied the British and the other allies besides. The tank program was, in a real sense, outrunning its own engine supply. Every hull that came off the line needed an engine, and there were not enough engines to go around. The Army needed another source of tank engines, a source that did not compete with the aircraft program, that could deliver in quantity immediately, and that did not require building whole new engine factories from scratch. And so, as it had in 1941, the Army turned to the automobile industry and asked the question that produced so many strange and brilliant answers. What do you already build, in quantity, that we could turn into a tank engine? Chrysler's answer was the strangest of them all. This is the paradox at the heart of the story. To build more tanks, America did not build a better engine, or a bigger engine, or a new engine. It built, in effect, no new engine at all. It took an engine that already existed, the ordinary 6-cylinder motor that Chrysler was already stamping out by the hundreds of thousands for its Dodges and Plymouths, and it simply used more of them per tank. 5 of them per tank, to be exact. The solution to the engine shortage was not to design a way to make tank engines faster, it was to redefine what a tank engine was, so that it could be assembled from the car engines that were already pouring off the existing lines in numbers nobody could match. The resolution of the paradox lies in the deepest logic of American war production, which was the logic of leverage. The single greatest asset America possessed was not any particular weapon or any particular engineering genius. It was the existing, enormous, humming machinery of mass production, the tooling and the supply chains, and the trained workforce that already built millions of automobile engines a year. The fastest way to make anything in wartime America was to find a way to make it out of things the automobile industry already produced. The Chrysler Multibank was the purest expression of this logic. It did not require a new engine factory because it used the existing car engine. It did not require new castings or new tooling for the cylinders because it used the existing car engine cylinders. It required only the ingenuity to take 5 of those existing engines and make them work together as one. And that ingenuity, it turned out, Chrysler had in abundance. The engine that looked like the most absurd improvisation of the war was in fact the most efficient possible use of the one resource America had more of than anyone else, the capacity to mass-produce automobile engines. The popular history, when it bothers to mention the multibank at all, treats it as a curiosity, a freak, the engine made of 5 car engines, and it usually stops there, with the image of the thing and a chuckle at its absurdity. It rarely explains how the 5 engines were actually combined, how 5 separate crankshafts could be made to drive a single output without tearing themselves and each other apart, how the firing of 30 cylinders was orchestrated, how the cooling and the lubrication and the fuel were managed across 5 engines that had each been designed to run alone. And it almost never confronts the central, surprising fact, which is that the thing worked, that it was reliable, that the intuition everyone had on first seeing it, the intuition that such a contraption must surely be fragile, was simply wrong. So this account will do what the others skip. It will explain the mechanism. It will show how the 5 crankshafts were geared to a central shaft, how the cylinders were arranged at their careful angles around the crankcase, how Chrysler took 5 engines that knew nothing of each other and synchronized them into a single coherent power plant. It will explain why the engine could keep running with 2 of its 5 banks completely dead, a survival characteristic that emerged directly from its 5-engine nature. And it will explain why the British, who received most of these engines, came to trust them, and why the men who actually had to maintain them after their first horror at the complexity came to respect the strange machine. Because the engineering is the point. To say the multibank worked is easy. To understand why it worked is to understand something real about the marriage of automotive mass production and military necessity. And that understanding is what the casual histories leave on the table. The company that built the multibank was Chrysler, and the man who led it was Kaufman Thuma Keller, whom everyone called KT. And to understand the engine, you have to understand the company and the man. Keller was born in 1885 in Mount Joy, Pennsylvania, to a family of Pennsylvania Dutch farmers. He did not come from money or from privilege. He trained as a machinist, learning to cut metal with his own hands, and he rose through the automobile industry on the strength of a machinist's instinct for how things were made. He understood manufacturing in his bones, the tooling, the tolerances, the processes by which a design became 1,000,000 identical parts. Walter Chrysler himself had hired Keller and groomed him and made him president of the Chrysler Corporation. And Keller carried on the engineering culture his mentor had built, a culture that was the envy of the entire industry. That culture mattered enormously to the multibank, because the multibank was not a problem that could be solved by a single flash of genius. It was a problem that had to be solved by patient, systematic, exhaustive engineering, by taking 5 engines that were never meant to work together and figuring out, detail by detail, how to make them do so. This was exactly the kind of problem Chrysler Engineering excelled at, and Keller, the machinist who ran the company, had exactly the right instincts to back his engineers when they came to him with a proposal that sounded, on its face, completely insane. He had already, in 1940, told the United States government that Chrysler would build tanks, despite the fact that, as he famously admitted, he had never in his life actually seen a tank. He had built the Great Detroit Tank Arsenal, the first purpose-built mass-production tank factory in America on 113 acres of Michigan farmland, and he had driven the first tank out of it one day ahead of schedule. When his engineers proposed bolting 5 car engines together, Keller, the man who understood manufacturing better than almost anyone alive, understood immediately why it might be the right answer. It used what Chrysler already had. It could be built now, and building now was what the war demanded. The engine at the center of it all was the Chrysler Flathead 6, the workhorse motor that powered the corporation's passenger cars. It was an L-head inline 6-cylinder engine, sometimes called a flathead because its valves sat beside the cylinders rather than above them, giving the cylinder head a flat, simple shape. It displaced about 251 cubic inches, with a bore of 3 7/16 of an inch and a stroke of 4.5 inches, a deeply under-square engine with a long stroke, the kind of slow-turning, torquey, durable motor that was standard in American cars of the era. It was utterly ordinary, the engine of the family Dodge and the family Plymouth, proven over years of production, built in enormous quantities, with all its tooling and its supply chains long since established and humming. A single one of these engines produced about 100 horsepower, which was fine for a car and nowhere near enough for a 35-ton tank. The tank needed something approaching 400 horsepower, which meant a single car engine was hopeless. But the engine had every other virtue the situation demanded. It was reliable. It ran on ordinary gasoline, not the scarce high-octane aviation fuel that some engines required. It was already in mass production, so it required no new factory, no new tooling for the major castings, no new supply chain. The cylinders, the heads, the pistons, the connecting rods, the crankshafts, all of these were already being made by the thousand. The only question was how to get 400 horsepower out of an engine that made 100. And the answer, the audacious, almost absurd answer, was to stop thinking about one engine and start thinking about 5. Now we arrive at the real engineering, the part the histories skip, the part that answers the question that the British mechanic and everyone else asked on first seeing the thing. How exactly do you take 5 complete, separate engines and make them into one? The conceptual answer is simple to state and very hard to execute. You arrange the 5 engines in a circle around a central output shaft, and you gear all 5 of their crankshafts to that single shaft so that their power combines. The execution is where Chrysler's engineering showed itself. At the center of the Multibank was a large cast-iron crankcase, and this central crankcase was the structural heart of the whole engine, the spine to which everything else attached. The 5 6-cylinder engine banks were bolted to this central crankcase in a careful circular arrangement, not a true radial, not a simple star, but a specific geometry worked out to make everything fit and balance. 2 of the engines were bolted to the lower part of the crankcase, one on each side, with their cylinders angled just 7.5 degrees above horizontal, lying almost flat. 2 more engines were bolted above those, with their cylinders angled 27 degrees above horizontal. And the 5th engine was bolted vertically at the very top. 5 banks of 6 cylinders each, fanned around the central case in a pattern that vaguely resembled the upper half of a radial aircraft engine, but was in truth something stranger and more particular. The arrangement made the engine compact in length, which mattered for fitting it into the tank, but dense and very heavy. Each of the 5 engines kept its own crankshaft. This is the crucial point, and it is the point the careless histories get wrong when they imagine some shared crankshaft. There was no shared crankshaft. There were 5 crankshafts, one for each engine, exactly as in 5 separate cars. What combined them was a gear train. On the front end of each of the 5 crankshafts, Chrysler fitted a drive gear, and all 5 of these drive gears meshed with a single large central gear mounted on the output shaft. The gears had herringbone teeth, a double-angled tooth pattern that runs smoothly and handles heavy loads without the tendency to push sideways that straight-cut or single helical gears have. 5 crankshafts, 5 drive gears, all meshing with one central gear, all their power flowing together into one output shaft that ran forward to the tank's transmission. That was the heart of it. 5 engines geared into one. Gearing 5 crankshafts to a common central gear is easy to draw and brutally hard to make work because of the problem of synchronization and torsional stress. Imagine 5 engines, each firing its cylinders, each delivering its power not as a smooth, continuous flow, but as a rapid series of impulses, a punch from each cylinder as it fires. Now gear all 5 of these pulsing, punching engines to a single shaft. If the impulses are not properly coordinated, the engines fight each other. The power pulse from one engine arrives at the central gear at a moment that conflicts with the pulse from another, and the result is a hammering, a torsional stress that loads the gear teeth and the crankshafts and the whole assembly with violent, irregular forces that can tear the engine apart. Chrysler's engineers had to solve this, and they solved it by carefully working out the firing order across all 30 cylinders and the precise phasing of the 5 crankshafts, so that the power impulses from the 5 engines wove together into a relatively smooth, even flow, rather than a chaotic hammering. The herringbone gears helped, distributing the loads smoothly. The phasing of the engines was arranged so that, in effect, the 30 cylinders fired in a sequence that kept the central gear under a steady, manageable load. This was not trivial engineering. It was the kind of detailed, systematic, calculated work that Chrysler's engineering culture was built for, the patient solving of a hard problem through analysis and testing. And when it was done, the result was an engine that ran smoothly, that delivered its power evenly, and that did not shake itself to pieces. The 5 engines, properly synchronized, did not fight. They cooperated, woven together by the gear train and the firing order into a single coherent power plant. The synchronization of the 5 crankshafts was the central engineering achievement of the Multibank, the thing that turned 5 car engines from a pile of parts into a working tank engine, and it is exactly the thing the popular histories never bother to explain. Beyond the synchronization, there was the problem of all the supporting systems, because each of the 5 engines had originally come with its own complete set of accessories, and running 5 separate sets of everything would have been the maintenance nightmare that mechanics feared. So Chrysler's engineers worked to rationalize and combine these systems wherever they could, taming the 5-fold complexity into something more manageable. Consider the cooling. Each of the 5 car engines had originally been driven by its own belt-driven water pump. 5 belt-driven water pumps, 5 belts, 5 potential failures would have been a constant headache. So the engineers replaced them with a single, more reliable water pump, driven off a jack shaft and gear drive that fed coolant to all 5 banks. 1 pump instead of 5. Consider the lubrication. Rather than 5 separate oiling systems, a single pair of oil pumps served the whole engine. 1 scavenge pump to pull the oil back from the engine banks, and 1 pressure pump to take oil from the reservoir and deliver it under high pressure to all 5 engine sections. 2 pumps centrally managing the oil for all 30 cylinders. The fuel system went through its own evolution. Originally, each bank had its own single-barrel carburetor sitting near it, 5 carburetors scattered around the engine, which made fuel distribution uneven and tuning difficult. The engineers eventually grouped all 5 carburetors together in one location, which improved the fuel distribution and made the engine easier to service. The ignition, the distributors, all of it was reworked and relocated to fit the new configuration and to be serviceable. The point of all this work was to take an engine that was, by its nature, 5 of everything, and to reduce the 5-ness wherever possible. To give the mechanics a single cooling system and a single oiling system and a manageable fuel system, so that the engine, for all its 30 cylinders, could actually be maintained in the field. It remained a complex engine, undeniably, but it was far less of a maintenance monster than the naive picture of 5 separate engines would suggest, because so much of the supporting machinery had been combined into single shared systems. This was the unglamorous, essential engineering that made the multibank practical, the patient work of taming the complexity, and it was a large part of why the engine turned out to be reliable rather than the disaster everyone expected. Let us put precise numbers to the finished engine, because the numbers convey the scale of the thing. The complete A57 Multibank had 30 cylinders arranged in 5 banks of 6. Each cylinder had the bore and stroke of the original Chrysler car engine, 3 7/16 of an inch by 4.5 inches. The total displacement was 1,253 cubic inches, which is about 20.5 liters, an enormous figure, the combined displacement of 5 automobile engines. It produced up to 445 horsepower at 2,400 revolutions per minute, with some sources citing peak figures as high as 470, and it generated about 1,060 pound-feet of torque. It had a compression ratio of 6.2 to 1, suited to the ordinary gasoline it burned, the same gasoline that fueled American cars, with no need for scarce high-octane aviation fuel. And it was heavy. The complete engine package, including its radiator, its great cast aluminum cooling fan, and its clutch, weighed 5,244 pounds. That is over 2.5 tons, heavier all by itself than many complete automobiles. The clustered arrangement made the engine relatively short, which was its saving grace for installation, but dense and enormously heavy. Its size and weight forced changes to the tanks that carried it. The hulls of the M3A4 Lee and the M4A4 Sherman that used the multibank had to be lengthened to make room for it, and the M4A4 in particular had a visibly longer hull than its siblings, stretched to accommodate the 30-cylinder monster in its tail. The engine was a beast by every measure, complex and massive and strange, but the numbers that mattered, the horsepower and the torque, were exactly where a tank engine needed them, and the engine could be assembled immediately from the car engines Chrysler was already building. That was the whole point of it. There was one characteristic of the multibank that emerged directly from its 5-engine nature and that turned its apparent weakness into a genuine strength. And it is worth dwelling on because it is the most surprising thing about the engine. Because the multibank was, in essence, 5 engines geared together, it possessed a remarkable redundancy. If 1 or even 2 of the 5-engine banks failed completely, whether from mechanical breakdown or from combat damage, the remaining engines could keep running and keep the tank moving. The multibank could reportedly continue to operate with as much as 40% of its 30 cylinders out of commission, 2 entire engine banks dead, and still move the tank. Think about what that meant in combat. A conventional single-engine tank that took a serious hit to its power plant or suffered a major engine failure was simply immobilized, a dead steel box waiting to be destroyed or abandoned. The multibank-powered tank had 4 backup engines. Lose 1 to a thrown rod or a combat hit, and you ran on 4. Lose 2, and you limped on 3. The redundancy that the 5-engine design provided, almost as an accident of its nature, gave the tank a survivability that no single-engine tank could match. This was the same kind of advantage that the General Motors twin diesel offered with its 2 separately clutchable engines, but multiplied, because the multibank had not 2 engines, but 5. The thing that looked like the engine's greatest vulnerability, its 5-fold multiplication of everything that could break, was in fact, viewed correctly, a 5-fold redundancy that made the engine more survivable, not less. The mechanics who first recoiled at 5 engines worth of complexity eventually came to appreciate that 5 engines also meant the tank could keep fighting when any one of them died. The 40% miracle was the multibank's hidden virtue, and it was a direct consequence of the very design that made it look absurd. The multibank went into production at the Detroit Tank Arsenal, the great factory in Warren, Michigan that K.T. Keller had built. The engine was first installed in a small number of M3A4 Lee medium tanks, just over 100 of them, as an interim measure. Then it found its real home in the M4A4 Sherman. Between July of 1942 and November of 1943, some 7,499 M4A4 Shermans with multibank engines were built. Adding the 109 Lees, the total number of tanks fitted with the A57 came to over 7,600. And Chrysler built nearly 10,000 of the engines in total, the extra ones serving as spares to keep the fielded tanks running, since an engine assembled from 5-car engines naturally required a robust supply of replacement parts at replacement units. The speed of all this was the entire point. Because the Multibank used the existing car engine and the existing tooling, Chrysler could produce it almost immediately without the long delay that designing and tooling a new engine from scratch would have required. The tanks flowed out of the Detroit arsenal, lengthened hulls and all, with their 30-cylinder engines in their tails at exactly the moment when Sherman production needed every engine it could get. The Multibank filled the gap between how fast America could build Sherman hulls and how fast it could build conventional engines to fill them. It was never meant to be the permanent solution. It was meant to be the engine that was available now in quantity while the better engines were brought up to full production, and in that role, it succeeded completely. It put thousands of additional Shermans into the field in 1942 and 1943, Shermans that would not have existed if Chrysler had not figured out how to make a tank engine out of 5-car engines. The United States Army, having received the Multibank-powered Shermans, made a decision about them that echoed the decision it made about the diesel Shermans, and for related reasons. The Army did not want the Multibank for its own combat use. The objection was complexity. 5 engines, however cleverly combined and however much their accessories had been rationalized, still meant more potential points of failure than a single conventional engine, still meant a more demanding maintenance regime, still meant mechanics who had to understand a 30-cylinder cluster of 5 motors. For an army that prized simplicity and standardization in its field equipment, the Multibank was more complexity than it wanted to take into combat, especially once the Ford GAA V8 became available as a simpler, more conventional, purpose-built alternative. So, the Army standardized on the Ford-powered M4A3 as its preferred Sherman for its own use, and it restricted the Multibank-powered M4A4 from American overseas combat. The M4A4 was classified, by the end of the war, as limited standard, the designation for equipment that was acceptable but not preferred. This was the same pattern that played out with the diesel M4A2. The Army kept the engines it considered simplest and most suited to its logistics, and it sent the others, the diesel and the Multibank, to its allies. The Multibank, like the diesel, became an engine that the American Army built but did not fight in. And once again, the Allies who received it found that the engine the American Army had declined to use was, in fact, very good indeed. The nation that received the great majority of the Multibank Shermans was Britain, and the British verdict on the engine was the opposite of the doubt with which it was first regarded. Britain, desperate for tanks throughout the war, received over 7,000 M4A4 Shermans, which they designated the Sherman 5, and they deployed them across every theater where British and Commonwealth forces fought, in North Africa, in Italy, in Normandy, and across northwestern Europe into Germany. And the British found the Multibank, to the surprise of many, to be a reliable and satisfactory engine. The reasons for the British satisfaction were partly about the British maintenance system, which was willing to invest the effort required to maintain the more complex engine properly, and partly about the genuine virtues of the engine itself once it was understood. It ran smoothly because the 30 cylinders, properly synchronized, delivered a very even flow of power. It was powerful and torquey. It ran on ordinary gasoline. It had the remarkable redundancy of its 5 engines, the ability to keep going with banks dead, and once the maintenance procedures were established and the mechanics trained, it proved durable and dependable in hard service. The British Sherman 5s fought through the desert and up the Italian peninsula and across the fields of France and the Low Countries, their 30-cylinder engines running reliably through years of combat. The mechanics, who, like Sergeant Hodges in our opening, had first recoiled at the sight of 5 engines in one tank, came to respect the strange machine because it did, against all their expectations, simply work. The engine that looked like a joke was, in British hands, one of the more reliable power plants of the war. There is an instructive counterpoint to the British acceptance of the Multibank, and it comes from the Soviet Union. The Soviets, who received and loved the diesel M4A2 Sherman, were offered the multibank-powered M4A4 for evaluation, and they tested it, and they rejected it. Their objection was precisely the complexity that the British had been willing to accept. The Soviets tested the M4A4, received the instruction on how to maintain an engine made of 5 separate motors, and concluded that it was too complicated for their field conditions. 5 engines meant 5 times the maintenance, 5 times the potential failures, 5 times the components that could give trouble in the brutal cold of the Russian winter when metal grew brittle and lubricants thickened. The Soviets wanted the 2-engine diesel, which they understood and trusted. 5 gasoline engines joined together, they did not trust. This divergence, the British accepting the multibank and the Soviets rejecting it, tells you something true about the engine, which is that it was a genuinely complex machine whose success depended heavily on the willingness and ability of its operators to maintain it properly. In the hands of a maintenance system prepared to invest the effort, like the British, it was reliable and effective. In the judgment of a maintenance system operating under harsher conditions and preferring simplicity, like the Soviet, it was more trouble than it was worth. Both judgments were reasonable because both reflected real truths about the engine. It was reliable when properly maintained, and it was demanding to maintain. The multibank was not a simple engine pretending to be complex, nor a complex engine that was secretly simple. It was exactly what it appeared to be: a sophisticated, complex, demanding, and, in the right hands, thoroughly capable power plant. And different armies, weighing its complexity against its virtues, reached different conclusions about whether it was worth the trouble. The lesson of the multibank is a lesson about the relationship between mass production and military improvisation, and about how the deepest American advantage in the war was not engineering brilliance in the conventional sense, but the ability to leverage existing mass production to solve new problems fast. Chrysler did not build the multibank because it was the best conceivable tank engine. It was not. It was heavy and complex and demanding. Chrysler built it because it was the engine that could be produced immediately, in quantity, from the car engines the company was already building by the hundreds of thousands. The genius of the multibank was not the genius of a beautiful design. It was the genius of leverage, of finding a way to turn the existing enormous capacity of the automobile industry directly into tank engines without the delay of building new engine capacity from scratch. This was the American way of war production, and the multibank was its purest expression. Faced with a shortage of tank engines, America did not pause to develop the perfect tank engine and tool up to build it. It asked what it already had, in quantity, and it found a way to make tanks out of that. The car engine became, by the audacious expedient of using 5 at a time, the tank engine. And thousands of additional Shermans reached the battlefield as a result in 1942 and 1943 when they were most needed that would not have existed otherwise. The multibank was ugly and it was complicated, and the American Army did not want it, but it put tanks in the field at the moment of greatest need, assembled from the engines America had in greatest abundance. In a war of production, the ability to do that, to turn what you already make in quantity into what you suddenly need, was worth more than elegance, and the multibank proved it. A number of A57 multibank engines survive today, preserved in museums and in the hands of collectors and tank restorers, and a few are still in running order, installed in restored M4A4 Shermans that occasionally run at military vehicle events. To see one running, or even to see one standing still with its 5 banks of cylinders fanned around the central case, is to understand immediately why the engine made such an impression on everyone who encountered it. It does not look like an engine. It looks like 5 engines caught in the act of becoming one, which is exactly what it is. A beautifully restored example was displayed for many years at the Walter P. Chrysler Museum, giving visitors a rare chance to see the strange machine in person before that museum closed. The survival of these engines and the fascination they hold is a small measure of justice for a power plant that was largely written out of the serious history. The multibank was strange, and strangeness is memorable, and so the engine that the official histories overlooked has found a kind of afterlife among the enthusiasts who appreciate exactly the audacity that made the official histories uncomfortable. 5 car engines bolted together is a thing people remember once they have heard it, because it sounds impossible, and because the further fact that it actually worked, that it was reliable, is more surprising still. The multibank has become, in the world of those who care about such things, a celebrated oddity, an emblem of wartime ingenuity at its most gloriously unconventional, the engine that should not have worked, and did. In a war decided by how many tanks you could build, America built more by making the engine out of the engines it already had. The Chrysler Multibank was 5 car engines, the ordinary 6-cylinder motors of the family Dodge and the family Plymouth, fanned in a circle around a central crankcase, their 5 crankshafts geared through herringbone teeth to a single central gear, their 30 cylinders firing in a carefully orchestrated sequence so that they wove their power together instead of tearing each other apart. It weighed 2.5 tons. It looked like a joke, and it ran smoothly and reliably, and it could keep running with 2 of its 5 engines shot dead, and it put thousands of Shermans into the field at the moment they were most desperately needed. It worked because Chrysler's engineers, under K.T. Keller, the machinist who ran the company, did the patient, unglamorous, systematic work that the casual histories never describe. They synchronized 5 crankshafts. They wove 30 cylinders into one firing order. They replaced 5 water pumps with 5 oiling systems with a single pair of pumps, and tamed the 5-fold complexity into something a mechanic could actually maintain. They turned 5 engines that knew nothing of each other into a single, coherent power plant, and they did it not because it was elegant, but because it could be done now with the engines America already built in greater quantity than any nation on Earth. In a war fought between systems of production, the system that could turn its automobile engines directly into tank engines by the simple, audacious expedient of using 5 at a time was the system that could build tanks faster than its enemies could imagine. The Germans built beautiful, purpose-designed tank engines and never had enough of them. The Americans bolted 5 car engines together and had Shermans to spare, enough to fight with and enough to give away to the British, who drove the multibank from the desert to Germany. The engine that the American army did not want and that the Soviets rejected as too complex, the British embraced and trusted and fought in for years. It was not the best engine. It was the engine that could be built now out of what already existed, and in 1943, that was worth more than perfection. 5 car engines beating as one carried the Sherman to war. It should not have worked. It did, and the doing was the whole point.